Hi everybody. Very good afternoon. How are you all? Yes, started finally. Okay, so as I always say, Andariki Namaskaram, Ellargu Swagatam, and a very warm Vanakkam to Vedantu J English channel. And today we are here to complete our inorganic chemistry now in class 12 boards. You only have two chapters, guys, and that is DNF block and coordination compound. P block has been removed, so you do not have P block. So two chapters basically we have to complete now, and three chapters we have to complete in the evening. I think that is doable. What do you guys say? What do you guys say? Yes. What do you guys say, everybody? Yes. Can we do this? Can we do this? Can we do this? Yes, we can, right? Yes, we can. Very good afternoon, guys. Vanakkam. So I also see that there are Tamil student supremacy here. Yes, I can guarantee that this session is going to be very jujupy stuff. You will see, and yes, we will also learn from our NCERT, because NCERT is our Bible for inorganic chemistry, everybody. So shall we start, everybody? Are we all here? You will get the notes, don't worry about it. However, I still suggest that please sit with a pen and paper so that you can solve the previous year question and you can get a clear picture of how the exam paper is going to be. Now, shall we start, everybody? Are you all sitting with a... Yes, I will be solving questions as well. Don't worry about it. There are a lot of questions that we're going to solve. Absolutely plenty of them are here. Don't worry about it. But I request you all that please sit with a pen and paper. So everybody is sitting with a pen and paper, guys? Everybody is sitting with a pen and paper? How long will this session be? God knows, Baba. When we finish it, then we will be done. I can't guarantee how long it will be, okay? Right now, see, if you are going to tell me that, ma'am, we did not have lunch, guess what? I did not even have breakfast because I was preparing the slide. So till now, I'm fasting. I have only had water and Vicks because I still have a running nose and I still have a broken voice. So yeah, we are also sacrificing and I need you guys to sacrifice. So don't go and tell me that, ma'am, we did not have lunch. Ma'am, we're feeling very hungry. Ma'am, I'm going to faint. Nah. Be strong now, okay? Be very strong now because we have to make sure that we get 75% in our class 12 board. So everybody, let's start. Chalo. All right, let us begin with our inorganic chemistry first chapter, that is DNF block, because DNF block is slightly easier and we can also predict the question. I'll tell you the most important questions as well. Then we will go into coordination compound. DNF block is basically the basic, the fundamental of coordination compounds. So let us start with NCERT. What do you all say? Right here is my NCERT book. And I gave you a task, everybody. Yesterday, I gave you a task and I asked you all to read your NCERT before you come to this class, okay? All right, so everybody, let us begin and let us start with our session. So, we see here, everybody, we see here that our NCERT book right here for D and F block, it starts with, read here, the D block of the periodic table contains the elements of group 3 to 12, okay, group 3 to 12. In which the d orbitals are progressively filled in each of the 4 long periods. What do we mean by progressively filled, guys? By progressively filled, that means we understand it is 3d1, then 3d2, then it is 3d3, like that, okay? It is going to be filled, correct? All right, everybody? Great. Moving on from here, we understand what it says is that the F block consists of elements in which 4f and 5f orbitals are progressively filled. That means 4f1, 4f2, 4f3, 4f4, 4f5, 4f7, 4f13, 4f14, like that. Okay. Alright, everybody. Now, they are placed in a separate panel at the bottom of the periodic table. The names, transition metals and the inner transition metals are often used to refer to the elements of D and F block respectively. So now, whatever you have read in this paragraph, can I just show you one picture and you will be absolutely clear? Yes, let me show you one single picture so that you understand what I am talking to you about, okay? Basically, they are right here in this paragraph. They are talking about what is D block and what is the P block. Now, everybody, if you look at the periodic table here, look at the periodic table, guys. Right here in the center, right here, this is your D block elements where you are progressively filling the D orbitals, right? And here is the separate panel where we are keeping the F block elements, isn't it? Here we are keeping the F block elements. So Your D block elements, they start from scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. Alright. And here you have yttrium to cadmium. Then you have lanthanum to mercury. Then you have actinium to copernicium. These are all your D block elements. And what did they say in the paragraph? They are writing that progressively D orbitals are filled. Okay. Alright, and here you have the 4f orbitals are filled progressively, and at the bottom one here 5f orbitals are filled progressively. Is this clear, guys? Can I quickly get some EPBT, that is easy peasy biryani tasty, everybody? Quickly go ahead and write down easy peasy biryani tasty in the chat box, that is EPBT, if the first paragraph of D and F block is absolutely clear for you. Yes, this session is going to be absolutely enough for your inorganic chemistry. I swear, I guarantee you that if you sit here for the next 2 to 3 hours, you will be able to get 30 on 30 in inorganic chemistry. Yes, this is clear, guys. Any easy peasy biryani tasty, everybody? EPBT? Yes, EPBT. Very good, very good, very good. Chalo, theek hai. Moving on, we are going to get back to the second paragraph now, and we are going to keep learning. Okay? Here now. Second paragraph. What does it write? The second paragraph says that, see, there are mainly 4 series of transition metal. The first one, scandium to zinc, is called as your 3D series, everybody. See, this is called as 3D series, guys. Whatever I'm writing, whatever I'm marking, you can also mark it in your NCERT. Okay? There are mainly 4 series of transition metal, 3D series, that is scandium to zinc, 4D series, that is yttrium to cadmium. Yes, and 5D series, lanthanum to hafnium to mercury, and 6D series, which has actinium, and elements from RF, that is rutherfordium to copernicium. So there are 4 D or D block series. Do we understand? Yes, do we understand? There are 4 D block series. The first one, that is scandium to zinc, is called as 3D series. The second one, that is yttrium to cadmium, is called as 4D series. Lanthanum to mercury is called as 4D series. No, sorry, 5D series. And the last one, actinium to copernicium, is called as the 6D series. Is this clear, everybody? Yes. Now, the 2 series of the inner transition elements, that is 4F, cerium to lutetium, and 5F, that is thorium to lawrencium, are known as lanthanoids and actinoids respectively. This is clear, everybody? Is this clear, guys? Is this clear? What to do after this session? Bro, chill man. Sit in the class. Sit in the class and wait up and focus up, please. If you keep asking me questions regarding future, you will not be able to focus in the present. Yes, please do that. Is this clear, everybody? Is this paragraph clear to you? Do we understand this, everyone? This paragraph, everybody, is it clear to you? Is this clear? Great. Okay, moving on to the next one. Okay, the next one is, see, the next paragraph says, originally the name transition metals was derived from the fact that their chemical properties were transitional between those of S and P block elements. Now, in the periodic table, the S block elements and the P block elements, they are called as the representative elements. Okay, that means they are the main elements of the periodic table. Now, when you are traveling from the S block to the P block, you are transitioning. The properties are transitioning. The properties are changing slowly and gradually to the P block. And that is why in the olden days, initially we started calling these guys as transition elements. However, the definition has changed a little bit. Okay. So originally the name transition metal was derived from the fact that their chemical properties were transitional between those of S and P block elements. Now, according to IUPAC, however, this is very important, everybody. This is absolutely important. Please, 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 please focus up, pay attention and note it down. This is the definition of transition elements that may come in your exam for 2 mark, everybody. Okay? So here, understand this. Now, according to IUPAC, transition metals are defined as metals which have incomplete d subshell either in neutral atom or in their ions. Mark this up, everybody. This is the meaning of transition metals. That means that they are supposed to have 3D1 to 3D9. They cannot have fully filled d orbitals at all. If they have fully filled d orbitals, they are not going to be called as transition metal. They are not going to be called as transition metals, which is why everybody, zinc, cadmium and mercury are not transition metals. They are only d block elements. Everyone pay attention. Everybody look at me. Focus up. Look at me. What did I say? Which ones are transition metals? Transition metal atoms are those metals. They have half filled, partially filled, incompletely filled d orbitals in their ground state or in their simple ionic form. That means that if you take away 2 electrons, if you take away 3 electrons, they are still supposed to have half filled, partially filled, incompletely filled d orbitals. But if you refer to zinc, cadmium and mercury, you will see that they do not have half filled, they do not have partially filled, they do not have incompletely filled d orbitals. Even if you take away 2 electrons from zinc, it will still have 3d10, which is fully filled d orbitals. That is why we do not call them a transition element. Is this clear, everybody? Is this clear, everyone? Yes. This is jujube stuff, guys. This is jujube stuff. Yes. Very good. Okay. Now what happens? This is exactly what is written here. See, zinc, cadmium and mercury of group 12 have full D10 configuration in the ground state as well as in their common oxidation state. Sorry guys, VIX. And hence they are not regarded as transition metals. So tomorrow, if they ask you an assertion reasoning question, or if they ask you a reasoning question, give reason to the following. Why is zinc, cadmium, mercury not considered to be a transition element? Then this line is exactly what you are going to write. Okay. All right. Now moving on. Acha, all the students who are telling me, ma'am, absolutely clear. Go fast. Let me tell you, bacha, if I go fast, then I will also have to do a halfway job, and then you will have to do self-study. Can we please focus up here in this class so that you again do not have to read inorganic chemistry? Can we do that? So please stay with me and trust me a little bit. Just trust me a little bit. I promise after this, if you sit for any sample paper, I guarantee 100 on 100 in inorganic chemistry. 100 on 100 in inorganic chemistry. Are you all with me? Will you all please trust me a little bit? Please trust me a little bit. Okay? Chalo. Okay. Moving on from here. However, being the end members of the 3D, 4D and 5D transition series respectively, their chemistry is studied along with the chemistry of the transition metals. Do we understand? Why? I mean, yes, we understand that zinc, cadmium and mercury, they are not transition metal atoms at all. They are not transition metals. However, they are present in the D block. They are the last elements of the 3D, 4D and 5D series. So we have to study them in the D block. But they are not transition elements. Reiterating it again and again. Okay? Yes. Okay? Cool. Okay? Yes. Ground state meaning. Ground state meaning, bacha. When a metal atom is absolutely on its own, you have not excited, you have not given it any energy so that it jumps to some other energy level. Ground state, it's the rest state of the metal atom, that is called as ground state. Got it? Okay, that is called as ground state. All right, now the presence of partly filled d or f orbitals in their atoms makes this transition elements different from that of the non-transition elements. Now this also they may ask you. What if they ask you that what is the major difference or major characteristic of transition elements? Why are they filled in a different block? That is because they have these partly filled, incomplete filled, half filled d orbitals, which is why their properties are much different than the s block and the p block elements, and we keep them in the d block. Okay, very good. Now the transition metal, okay, the transition elements and their compounds are studied separately. However, the usual theory of valence as applicable to the non-transition element can be applied successfully to the transition elements also. This is not a very important line. Forget about it. Okay? Various precious metals such as silver, gold and platinum and industrially important metals like iron, copper and titanium belong to the transition metal series. And in this unit, we shall first deal with the electronic configuration, occurrence and general characteristic of transition elements, with special emphasis on the trends in the properties of the first 3D transition metals along with the preparation and properties of some important compound. This will be followed by consideration of certain. Anyway, so in this part, basically the chapter is giving you an overview. They're telling you that in the upcoming pages what we are going to learn. Okay, what we are going to learn. Cool. But before we begin with the whole chapter, let us quickly go and take a look at the periodic table once again, and let us quickly revise what are the things that we have studied, everybody. So what are the things that we have studied, guys? We have studied that this is your S block, this is your S block, and this is your P block, right? The S and the P block, they are called as representative elements. They are the main blocks of periodic table. In the olden days, we named this D block elements. This right here in the middle, they are called as D block elements. We call them to be as transition elements because the properties were transitioning from S block to P block. However, the main IUPAC definition came much later, and it said that no, actually, these D block elements, these guys, they have half filled, they have partially filled, they have incompletely filled D or B orbitals, and that is why they are called as transition elements. However, here if you see, zinc, cadmium, mercury, these are not considered a part of the transition elements, but they are a part of the D block. Getting it? Yes. So you have read that there are 4 D block elements, scandium to zinc. This is your first D series, that is called as 3D series here. Yttrium to cadmium, this is your 4D series, everybody. Lanthanum to mercury, this is your 5D series. And finally, you have actinium to copernicium, which is your 6D series. So there are 4 D block series and there are 2 F block series. This is your 4F series and this is your 5F series. Okay, from lanthanum to lutetium is 4F series. Actinium to lawrencium is your 5F series. Okay, all right. Yes, guys, copernicium, it's not written in the NCERT. Nobody will ask you any question about NCERT. What is written, focus on that. Don't go and predict the question, guys. I'm telling you, focus up. Okay? Nobody is asking about copernicium. Copernicium, the details about copernicium is not given in the NCERT, so we will forget about it. Okay? Now, are we all clear, everybody? Are we all clear? Lanthanum and actinium, they belong to D block elements. Lanthanum and actinium are just the leaders of the F block elements. They are not a part of the F block element. They are actually D block elements. Okay? Alright? Yes, guys. Moving on, everybody. Now let us go back. Yes, so are we all clear? Are we all clear, guys? Yes? Are we all clear? Yes? Okay. Great. Okay. Srusha, this is just a showcase. They are a part of D block elements. Aren't you listening? Listen, no, bacha. Don't make it, don't delay it. Okay? Yes, do not delay it. Okay? Yeah. Okay, guys. Moving on. Now, let us try and understand the properties of D block. Shall we? Shall we, everybody? Are you all with me? EPBT? Yes. Great, great. Yes, you will get this whole PDF. This whole PDF, I'll send it to you in the Telegram channel. Don't worry. This whole PDF, I'll be sending it to you in the Telegram channel. Okay? Okay. Okay. All right, guys. Now, so the first thing, let us talk about the position. The position in the periodic table, we have just seen that the D block occupies a large middle section of the periodic table. Between S and P blocks in the periodic table, the D orbitals of the penultimate energy levels of atoms, electrons give rise to 4 rows of all this. Okay, now here is a word, guys. The word is penultimate. Okay, what is penultimate? You remember how to draw a structure of atom, everybody? So let us suppose that this is your nucleus, right? Then you will have S orbital, you will have P orbital, you will have D orbital, you will have F orbital, right? Blah, 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 like this. So this last shell, we will call this to be as ultimate shell. What do we call it? We call this to be as ultimate shell or ultimate energy level. But this, the one that is the second last, the one that is just inside the ultimate shell, that is called as penultimate shell. What do we call this? This is called as penultimate shell or penultimate energy level. Do we understand this, everybody? Do we understand this, guys? Yes? Do we understand this? Great. Okay. All right. So, guys, I can see a lot of questions here. Okay. Expert Ninja is telling me, ma'am, can you teach PYQs on the coordination compounds? Bacha, did you see the video that I took yesterday? I told you clearly that we will be doing PYQ. You don't believe me? Let me show you. Here are the PYQs. See, I have brought to you everything, but I guess you guys are just not giving me enough time. See, this is a PYQ, guys. These are all PYQ. Do you see? It's written here, PYQ. So yes, we do have PYQ. Okay? Yes, we do have PYQ. How long will the video go? I do not know, Charan. I do not know. I'm hoping it will take me 2.5 hours to 3 hours to be able to complete 2 chapters. But I'm not very sure. It might take longer than that. Whenever the chapters will be over, whenever I am satisfied that you know the answer, when you will be satisfied that yes ma'am, inorganic chemistry is done, that time we will be done. Okay, Charan? Alright, I can't tell you. Ritis, now, Ritis, have you seen that I have already reached oxidation state? I have just started the property. So, bacha, wait up. What I will suggest is that why don't you get some popcorn, get some lunch of yours, start writing it down, focus up in the class. I promise, after the class is over, if I do not complete something, please complain. Raise a complaint against me and Vedantu, I do not care. But right now, can you please focus up? Give me some time. Yes? Imagine this is a movie. Oppenheimer movie was 4 hours long, right? So wait up. I promise I will complete each and everything. Common oxidation state, penultimate shell, standard electrode potential, everything. Potassium dichromate, potassium permanganate, everything. I will do all of it. I will do all of it. Okay? Now can you please stay with me, everybody? Can you please stay with me? Yes? Please stay with me. Can we? Everyone, will you be with me now? Yeah? Okay? Yes. I will start teaching. You guys do not write these kind of questions that ma'am, please do this, ma'am, please do that, ma'am, please do this, ma'am, please do that. I'll do it. All of it. I'll do it. Pakka. Yes, I'll do it. Yes. I'll do it. Chalo. Scared to death? Arey, no, Baba. Don't be scared. That is why I'm here. No. Why do you think I'm here? Okay, can I show you certain things? Wait. Wait, you guys are scared, no? You are telling me. You guys are scared. Shall I show you something? Look at this. Look at this, how my hands are shivering. I'm telling you I'm not well. Like literally, I'm still not well. Look at this, how my hands are shivering. Do you see? It's not steady. I'm not able to hold the pen. It's shivering, see. The moment I hold the pen, it's shivering. So I'm here. Today I am here the whole day just so that I can give you the best content that is possible. So please wait up. I'll tell you each and everything. Don't worry about it. Whatever doubt you have, Kim Taeyung, don't worry. I'll tell you, bacha. I will tell you. Okay? So now, please stop the chat. Be here with me. I have closed nose. I still have a Vicks in my mouth. And I have like couple of Vicks that I have kept right in front of my desk. Yes, because I'm not well. I have fever. I've taken a Saridon now. Just now I've taken a Saridon after drinking a little bit of coffee. So yes, I'm here. Just chill, guys. I'm here with you. I'm here. Okay? Yes, NEET students can also watch it. Okay? Thank you so much. Now be here with me. I'll explain each and everything. See, I'm explaining you penultimate shell. Now this is so basic that you should probably know this from your 10th standard. Actually, you should know this from your 10th standard. But see, I'm teaching you, right? I'm teaching you from the basic. So just trust me. I'm here. Okay? Yes, Bhavani, you should. Okay? You should. Focus now. Focus. Everybody, focus up. So tomorrow, 27th, when you are going for your exam, what should you remember? For inorganic, remember my face. Every time you're forgetting an answer, just remember my face. That's what Nabamita Ma'am was doing. Yes? And you will be able to understand everything. So, chalo guys. Chalo. Okay. Alright here. So, what does this paragraph say? This paragraph is telling us that the D block occupies the large middle section, which we have seen, right? in the periodic table. This side is S block, that side is P block. In the middle, large flank of the periodic table is taken care by D block. है ना? Then they say that the D block of the penultimate energy level of atoms, they receive electrons one by one. Obviously, scandium has what electronic configuration? 3d1. Titanium has what? 3d2. Vanadium has what? 3d3. Chromium has what? 3d5. Manganese also has 3d5, right? Like this they have. So as they keep getting electrons, they are filled like that. And because they are filled like this, that is why we get to see 4 series. There is 3D, there is 4D, there is 5D, there is 6D. Right? These series you get to see. Okay? Alright, and here they are saying that the d orbitals of the penultimate energy level of atom receive electrons giving rise to 4 rows of the transition metal. Yes, this is clear, guys. This is clear, everybody. Very easy. Do we understand what is ultimate shell and penultimate energy level? Is there anything, any doubt here? Everybody, do we understand this? This paragraph, do we understand this, everybody? Yes or no, guys? Yes or no? Yes or no? Yes, we do. Great. Okay. Now, moving on. Let us talk about the electronic configuration. Guys, this is very, very, very important. Electronic configuration, you must have it in the tip of your tongue. Okay? Alright. Chalo. Okay. In general, the electronic configuration, please have a look, everybody. In general, the electronic configuration of outer orbitals of this element is n-1 d 1 to 10 ns 1 to 2. What is the general electronic configuration? The general electronic configuration, my dear student, is general electronic configuration. What is it? It is n-1 d 1 to 10 ns 1 to 2. This is your general electronic configuration. Okay? Write it down. Write it down, everybody. Yes? Okay. Now, except for palladium. Palladium has an electronic configuration. Note it down, everybody. Palladium has an electronic configuration of 4d10 5s0. Now, Kim has asked, okay, Kim had asked me that, ma'am, silver has full electronic configuration. How come that is a part of d orbital? How come that is a part of d block element? Now tell me, palladium also has fully filled d shell, fully filled d orbital. How come palladium is a d block element? They may ask you. They may ask you. You tell me. How come palladium is a general electronic how come palladium is a d block element? Now, coming back to the definition, guys. What was the definition? The definition of the d block element was, the definition of transition element was, they are supposed to have partially filled, half filled, incompletely filled d orbitals in their ground state or simple ion. Now, if I take away 2 electrons from palladium, what will I get? Let's say that palladium in its general form, right? Palladium in its ground form has 4d10 5s0, correct? But what if I take away 2 electron, palladium plus 2, then what will I get? 4d8. That's a simple ion. Pd2 plus, simple ion. The simple ion incompletely filled, na? This is incomplete filled, right? 4d8 is incompletely filled, my dear bachus. That is why palladium is a transition element. Clear hai? Clear hai? No, Kishore, this is a transition element. The only non-transition elements present in D block are zinc, cadmium and mercury. Okay? Alright? Yes. Okay. Now, the n-1 stands for inner d orbitals, which may have 1 to 10 electrons, and the outermost ns orbital may have 1 or 2 electrons. That is exactly what we are understanding from this general electronic configuration. See, the general electronic configuration is n-1 d 1 to 10. That means it is 3D or 4D or 5D or 6D. It can be 6D1, 6D2, 6D3, 5D1, 5D2, 5D3, 4D1, 4D2, 3D1, 3D2, like that it can have. And in ns1 to 2, that means 4s, 5s, 6s, 7s, there you can have 1 or 2 electrons, because s orbital, what is the maximum electrons that can be present in s orbital, guys? 2 electrons. So that is what the paragraph is saying, isn't it? Yes. But Vishal Bacha, how does it matter if it is just about ground state? I told you clearly, the definition says that ground state or common oxidation state. In case of zinc, in ground state, it is fully filled. In common oxidation state, that is Zn plus 2. Even if you take away 2 electron, it will still have fully filled d orbital, which is why they are not transition element. But palladium is, because in palladium, ground state is fully filled d orbital, but in common oxidation state, it can give you partially filled d orbital. Cool? All right, everybody. Yes. Your book does not have PD, no problem. Just Sukit Rani, can you just write it down in a notebook? I think it will help you. Okay? Alright, this is understood. However, this generalization has several exceptions because of very little energy difference between n-1d and ns orbitals. What do we mean? Now, we are telling you in this sentence that generally electronic configuration is this, but there are exceptions in their electronic configuration in the d block elements, because this everybody, because this ultimate shell and the penultimate shell, right, this energy gap is actually very small. You know how I always give you this example? Let us take a story, everybody. Let us say that Vishal and Mitali, okay, Vishal and Mitali, let's say, are the toppers in the class usually, okay. Let's say that this unit test Vishal got 49.5 out of 50, okay, and Mitali got 49. What is the difference? The difference is very low between the first topper 1 and topper 2, right? Right, everybody? Yes or no, guys? Yes or no, everybody? Tell me something. Is that right, everybody? Yes, very good. Cool. Now, what happens is the Vishal cannot take a chill pill. Vishal cannot think that, ayyo, from tomorrow I will chill because I'm anyway the topper. Who is going to beat me? But that's not the case, because Mitali was the second topper just by 0.5 marks. Just by 0.5 marks, Mitali was the second topper. Now, Mitali studied a little bit more and Mitali became the topper one. So, both Vishal and Mitali, they cannot take a chill pill. Either one of them will become the topper very fast, right? So, the gap, the energy gap, the marks gap is very little. That is why anybody can participate in the topper, in becoming a topper. Similarly, here what happens is the d orbital and the last s orbital, that is 4s and 3d, the energy gap is so small that the 4s are like, hey, I am the ultimate shell. The 3d shell will be like, bro, the energy gap is too little. You think that you will always be the topper, huh? I will come and I will also participate with the electrons. Getting my point? Getting my point here? Yes. So that is why you get to see these exceptions here. Now coming back to palladium, why is it that palladium is an exception? Why is it that palladium's electronic configuration is not 48 5s2? That is because now 5s is a little higher up. 5s. Now coming back to this question, imagine if we ask Mitali that, Mitali, why were you the second topper? Why couldn't you bring that 0.5 marks and you could not beat Vishal? Mitali will be like, I'll do it next time. Right? Mitali might say that. Mitali might say that I'll do that next time. Similarly, here what happened, the 5s is a little higher up, and d orbitals, they are the most stable when they are fully filled or when they are half filled. Either you should have d5 or you should have d10. Then they're very happy. They're very happy. So palladium, instead of keeping itself 48 5s2, it was like, you know, I want to be a little happier in life. So I will have d10 and 5s0. Who cares about s? After all, they are d block elements. Nobody cares about the s orbital here. We care about the d orbital here, and that is why this palladium, they were like, okay, we will have fully filled d orbital in the ground state. Common oxidation state, we might want to give away electron, nobody cares. But right now in ground state, we will have fully filled. So now, guys, do we understand that why do we have exceptional electronic configuration of some elements in d block? Yes or no? Yes or no, everybody? Yes, guys. Can we do this? Can we understand this? Why is there a lot of, why is there a lot of exception? Yes or no, guys? Yes or no? Yes. ठीक है. Now, similarly, you will find everybody, see, look at me here. Furthermore, half and completely filled set of orbitals are relatively more stable. I have just explained that D5 and D10, they are more stable. A consequence of this factor is reflected in the electronic configuration of chromium and copper. So if you look at chromium and copper in 3D series, you will find that chromium, instead of having 3D4 4s2, chromium does not have 3D4 4s2. Chromium has an electronic configuration of 3D5 4s1. Similarly, copper does not have 3D9 4s2. Copper does not have 3D9 4s2. Copper has 3D10 4s1. Okay. Copper has 3D10 4s1. Alright. Yes. So the ground state electronic configuration of the outer orbitals of transition elements are given here. These are the ground state elements, everybody. Now let me write down the electronic configuration so that you get a clear picture what is written here in the table. See, for scandium, they are saying that atomic number, Z is atomic number, right? 21. If it is 21, then what is the electronic configuration? The electronic configuration of scandium is C. From here, I can write it 3D1, 4s2. See, 3D1, 4s2. Do you see? Very good. Now, for titanium, everybody, for titanium, it is 3D2, 4s2. Alright, for vanadium, it is 3D3, 4s2. Okay. For chromium, it is 3D5, 4s1. This is an exception, right? Then we come across manganese, which is 3D5, 4s2, everybody. All right, everyone. Yes. Then we come across iron. Iron is 3D6, 4s2. Okay. Then we come across cobalt. Cobalt is, my dear students, 3D7, 4s2. Nickel is 3D8, 4s2. Now here we will come across another exception, that is 3D10, 4s1. This is another exception. And last but not the least, zinc will be 3D10, 4s2. This electronic configuration, I want you all to note it down right now, and please, okay, please, yes. Please note it down, everybody. Note it down, okay? All right, chalo guys. Moving on from here. Similarly, for the second series, that is yttrium to cadmium, also you have the electronic configuration. Let us write that down, everyone. For yttrium, it is 4D1, 5s2. All right, yes. For zirconium, it is 5s2, 3D. 5s2, 4D2. Sorry. 1 second, guys. Here, writing it down. What is it? It is going to be 4D2, 5s2. Okay. Then we have niobium. Niobium is going to be 5s1. Sorry, 1 second. Wait a second. I'm getting a little confused here. 1 second, huh? Sorry, I've written 4D first, right? Huh? So niobium has 4D4 and 5s1. Okay, see, this is an exception. All right. Molybdenum, everybody, has 4D5 and 5s1. Okay. Technetium, everybody, has 4D6 and 5s1. All right. Ruthenium has 4D7, 5s1. Yes, rhodium here has 4D8, 5s1, and like that you can form the electronic configuration for each and every element. But let me still give you the ones that have a different electronic configuration, that is niobium, molybdenum, technetium. All right, yes, ruthenium, RH, PD and Ag here, these guys, they have a different electronic configuration. All right, everybody, is this clear, guys? Is this clear? Okay, now can you all quickly give me a little bit of moment, because I need to go to the washroom. Can I just go to the washroom and come back? Can you take a break? Yes, guys, can we take a break for like 5 minutes? I'll just come from the washroom. Can I do that? Can I do that, everybody? Till then, I request you all to just go through the electronic configuration and write down in your notebook. Write down all the electronic configuration in your notebook. I will come back and I will tell you all the other things, okay? Can you all do that? Coming back, guys, coming back. In 5 minutes, I'll come back, okay? All right, here we are, guys. Here we are. Back. Chalo. So this was the electronic configuration that we are talking about, right? So these are the ones that you have to specially note it down, because these guys, they have slightly exceptional electronic configuration. Once again, reiterating it, everybody, I'm taking a little bit time in the basics of the DNF block, because then we can be a little faster when we come to coordination compounds and when we go a little further into DNF block. Once again, why does this exception arise? That's because the D block elements, they have a very competitive energy gap between the 3D and the 4s. Both the ultimate shell and the penultimate shell can participate in electron donation. That is why we have such exceptional electronic configuration. Are we clear, everybody? Are we clear, guys? Yes? Yes, why 3D10 4s1 is an exception? Because 4s1, it is supposed to be usually 4s2, right? Generally, we see that in the 3D series, we know that what is it? It is 3D1 4s2, 3D2 4s2, 3D3 4s2. But the moment you get to chromium, you see that it is 3D5 4s1. For copper, it is supposed to be 3D9 4s2, but it is 3D10 4s1. That is why it is an exception. So Parthiv, Pranav, everybody please pay attention. You guys are not paying attention. The same thing, I'm repeating it twice, thrice, 5 times. Please pay attention. Now, everybody, if you look at it, so the general electronic configuration we have spoken about. Now, let us move ahead. The electronic configuration of outer orbitals of zinc, cadmium, mercury and copernicium, they are represented by the general formula N-1D10NS2. Okay, this is the general formula for zinc, cadmium, mercury and copernicium. What is it? N-1D10NS2. Okay, the orbitals in these elements, they are completely filled in the ground state as well as in their common oxidation state. Therefore, they are not regarded as transition elements. This sentence, guys, is very important. This paragraph is very important because it explains why zinc, cadmium, mercury, copernicium, they are not regarded as transition metals. All right, everybody, moving on. The d orbitals of the transition elements, they protrude to the periphery of an atom more than the other orbitals, that is S and P. What does it mean? Protrude means they are coming out of it. For example, let's say that what will happen, imagine if this is a metal, okay, if this is a nucleus or this is an atom. So what happens is, let's suppose that you have, okay, so let's suppose that this is our s orbital. Wait a second. Let's suppose this is our s orbital. So this s orbital will be just like this here, right? Can you see it? This s orbital is protruding, that means coming out of the nucleus just this much. Coming out of the nucleus just this much. But when we talk about d orbital, the d orbital is protruding like this. It is coming out of the nucleus a lot more than the s orbital. This is exactly what is explained here. Once again, guys, let us read it. The d orbitals of the transition elements protrude to the periphery of an atom more than the other orbitals, that is S and P. Hence, they are more influenced by the surrounding as well as they affect the atoms or molecules surrounding them. Because the d orbitals are protruding, because the d orbitals are out of the atom, right? They're like, you know, they're always looking at, they're like the security guard of the boundary of atom. So because they are looking outside all the time, they influence the surrounding, they influence their own surrounding, and they get influenced by the surrounding atoms and molecules. Do we understand, everybody? I didn't know Baba, s orbitals are not pink. What is wrong with you guys? Hat paglu. What is this paglu questions you are asking, huh? Have you like completely kept your brain in the refrigerator and then you have come to the class, or what? It was an example. It was an analogy. Oh my God. My God. Just because I took a pink clip to show you. So d orbitals are white in color or what? Muhil. Bacha, I mean. Oof. Teaching you guys is a task, yeah? Teaching you guys is a task. Seriously. Amma. Oh God. Okay. Anyway, guys, moving on. See. Now, in what respect? So I understand that this statement, it says that they can influence others and they get influenced, but in what respect are they influencing? What is it that they are influencing, that this is happening here? Okay, let's understand. See what happens here. Okay, so in some respect, ions of given dn configuration, that is n is equal to 1 to n, they have similar magnetic and electronic properties. Okay, with partly filled d orbital, these elements exhibit certain characteristic properties such as display of a variety of oxidation state, yes, formation of colored ions, and entering into complex formation with variety of ligands. That is what we are about to read in the coordination compounds chapter. Now, the transition metals and their compounds, they also exhibit catalytic property and paramagnetic behavior. All these characteristics have been discussed in detail later in this unit. There are greater similarities in the properties of the transition elements of horizontal row in contrast to non-transition elements. Now, if you look at P block, do you really find much similarities between aluminium, then what do you have? Then you have, silicon, then you have selenium, then you have phosphorus, then you have chlorine. Do you find similarities between all these elements? Not so much. But here in this row, you will find much similarities. That does not happen with the non-transitional elements, but in transition elements, you will see that there are lot of similarities. Cool, everybody? Moving on from here, okay? Yes, however, some group similarities also exist. We shall first study the general characteristic and the trends in the horizontal rows, particularly the 3D row, and then we will consider some group similarities. Now, guys, we will also solve the example and the in-text question, everybody. So let us take a look at it. On what ground can you say that scandium is a transition element but zinc is not? What is the answer, everybody? Can you quickly write it down in the chat box, everyone? Yes. Quickly write it down in the chat box and quickly go call up your friends, everybody. I'm seeing that some of the students are leaving the class. This is not good. You need 75% criteria. Let me remind you, everyone. Quickly go and call up your friends, everybody. Yes. Come on. On what ground can we say that scandium is a transition element but zinc is not? I'm going to cover this whole up. I wish I could cover this whole up. Like this, I'll cover it up. I'll cover this up, guys. Come on, quickly. Quickly let me know, everybody. The answer is on the basis of incompletely filled 3D orbitals. For scandium, it is 3D1, 4s2. But for zinc, it is 3D10, 4s2. So even if you take away 2 electrons, it will still be in 3D10. Zinc has very good, and introverted Slytherin, very good. Tarun, what does common oxidation state mean? I'll come to that. Don't worry about it, okay? We will tell you, okay? Yes, everything, Balaji, everything. All the questions from NCERT, you must solve it. Now, so somebody had asked me, silver atom has completely filled d orbitals 4d10 in its ground state. How can you say that it is a transition element? Let us take a look at silver, everybody. Silver is right here, isn't it? This is your silver. So silver's electronic configuration in ground state, everybody, is silver. See, silver's electronic configuration is not 3D, it is 4D. Silver's electronic configuration is 4d10 and 5s1. But if I take away 2 electrons, what if I take away 2 electrons from silver? If I take away 2 electrons from silver, then what will happen? What will happen, guys? Silver will get into a configuration of 4d9, and that is incompletely filled. That is partially filled. That is not completely filled d orbital. So that is your answer, that silver in its common oxidation state, it has partially filled or incompletely filled d orbitals. That is why it is still considered as a transition element, and it is not just a d block element. Is this clear? This answer I have just told you, guys. Will you all be able to write it down? I've just told you this answer, guys. Will you all be able to write it down? Yes? Very good. Very good. Kajal, Srusha, Nikita, Kashi, Nevi. Very good. Very good. Rear. Very good. Yes. Sai Sunesh. Well done. Aishwarya. Very good. You guys are doing an amazing job. Amazing job, everybody. Chalo, moving on now. Now let us talk about the physical properties. And guys, whoever wants to scold me and tell me that, ma'am, you are going very slow. You want marks in inorganic chemistry, right? let me tell you, inorganic chemistry, the only way to study is NCERT, and we are going to dive deep into NCERT. We're going to go through each and every table. We are going to go through each and every line in NCERT, so that tomorrow you come back after your chemistry exam and I want you all to let me know that, ma'am, thank you so much. I just want that. That will show me, that will be my validation of my work. That is how I will understand that yes, I have done a good job. So stick to the class till the end, guys. We are going to get that full marks in inorganic chemistry. Okay, everybody? Yes. Chalo. Now, guys, let us understand, everyone, physical properties. Nearly all the transition elements, they display what? They display typical metallic properties such as high tensile strength, ductility, malleability, high thermal and electrical conductivity, and metallic luster. Now, what are these metallic properties, guys? High tensile strength. What do you mean by tensile strength? Tensile strength, let me explain this to you, okay? Imagine this is a imagine this is a metal wire. This is a metal wire, and if I try to bend it, okay, if I try to keep some weight and bend it, you see that the tendency to break apart, that's very less. The tendency to break apart is very less, and that is called as high tensile strength. Have you seen the Worley Sea Link in Bombay? You know those cable wires that you have? They are actually metal. Why? Because the metal wires, they will be able to hold the bridge even if there is a big, huge, heavy vehicle that is running. The tendency to break apart is very less, and that is called as high tensile strength. Got it? Clear? Very good. Yes. So nearly all transition elements, they display high tensile strength, apart from that ductility. What is ductility? Ductility is the tendency to convert them into wire. What is malleability? Malleability is the tendency to beat them like this with a hammer and make them into thin sheet. That is why aluminium is a metal. You use aluminium foil, right? What is it? It's a thin sheet. Exactly. Gold. You see gold jewelry. Why? Because intricate designs can be made into gold. Gold is very malleable, very ductile. That is why we use gold here. Cool? Okay. High thermal and electrical conductivity. Bro, you tell me, guys. In your house, whatever you have, do you have electricity? Do you have fan running? Do you have tube light running? Do you have lights running? What is the wire? The wire is made up of metal. What is the metal? Copper. Usually, what is copper? Copper is a D block element, you see? Yes, and the kitchen utensil. What do you have in the kitchen utensil? You have steel, you have iron, cast iron, dosa tawa, don't you have? Don't you guys have cast iron dosa tawa? That is where we made dosa, isn't it? And the idli stand that you have, idli stand is made up of what? It is made up of what? Exactly, all metals. So do we understand here? Yes, we do. Correct. Okay. Now, and they have metallic luster. What is metallic luster? Guys, come. Metallic luster, we all know, right? The metals, they shine. The metals, they shine. Obviously, there are other non-metals also which shine, but we all know that metals, they shine. So, metallic luster is something that is characteristic of the metals. Okay? Now, with the exception of zinc, cadmium, mercury and manganese, they have one more typical metallic structure at normal temperature. Now, here they are talking about the lattice structure of transition metals, which I'm pretty sure they will not ask. However, if you want, you can definitely go through this table, everybody. Yes, this table, just go through it once. However, I am pretty sure they will not ask you because solid states has been deleted from your syllabus, right? And this is basically, you know, the HCP packing, the BCC packing, those are belonging to solid state. So I'm pretty sure they will not ask you. However, if you want, you can go through this. Okay. However, you can go through this. Darsh, virtual punch or virtual slap you will get. Don't ask me all of that question. Please, yeah. Please tell me you are all 10th pass. I will cry otherwise. Now what? Anyway, my hands and, my legs will shiver and I'll just fall down, guys. Come on, don't do that to me. Okay. Moving on, everybody. Acha. Now, very, very, very important, everybody. Please focus up, everybody. Call up your friends, everyone. Quickly call up your friends because all these while it was the trailer, but now the actual picture starts. This is the climax of the movie, everybody. Right here, these graphs I have seen in the exam, everybody. Quickly call up your friends. Tell everybody to be here. Nobody move out of the class now. Okay? Whoever is here, nobody move out of the class. You want to have lunch, you're going to sit in the class and have lunch. Okay? Do not leave the class. I swear and I'm telling you that do not move out of the class now. Okay? Very important. Okay. Now guys, what happens is the transition metals, with the exception, once again everybody, whenever we talk about the transition metals, we are not talking about zinc, cadmium and mercury. Yes, so all the other elements, all the other transition metals like, you know, your iron, your cobalt, copper, right? They are very hard and they have low volatility. What is volatility? You know, alcohol is very volatile. What does alcohol do? Alcohol is very reactive. Alcohol, the moment you keep it on a surface, if I keep sanitizer on my hand, what will happen? It will go away. But if I keep copper in my hand, will it evaporate and go away? No, not at all. It will not go away. The copper will stay right there, isn't it? Yes. So this is what we are saying, that all the other metals, they are not volatile. Okay? Their melting point and boiling points are high, and figure 8.1 depicts the melting points of transition metal belonging to 3D, 4D and 5D series. Now guys, let us have a look at this 3D, 4D and 5D series. Everybody here. Everyone, have a look. So this is your 3D series, my dear students. This is your 3D series. You have titanium, vanadium, chromium. Do you see that chromium has a very, very, very high melting point compared to all the other 3D series? That means compared to scandium, titanium, vanadium, manganese, iron, cobalt, nickel, copper, zinc. Compared to all the other 3D elements, chromium has a very high melting point. Can you attribute it to something? Can you tell me the reason why chromium does have a very high why chromium does have a very high melting point? I almost told you the answer. Because, my dear students, chromium has an electronic configuration of 3d5 and 4s1. If you look at it, all these electrons are unpaired. All these electrons are unpaired, my dear bachus. If I draw the d orbital here, 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5. And this is your 4s, right? All of these, they have space to accommodate another electron, right? All of them, the electrons can be paired up in one shell, isn't it? Yes. So you can pair them up, but it is not paired. All of them are unpaired electrons. These unpaired electrons, they will be donated in the kernel of the metal. They will be donated in the lattice of the metal. And that is why there is a very strong bonding that is happening, which even if you heat it, it takes a little more time to break it apart. That is why chromium has very high melting point. Okay? Chromium has very high melting point. Similarly, if you go to the 4D series, you will see that molybdenum has very high melting point. And if you go to the 5D series, you will see that tungsten has very high melting point. Now do you understand why in the bulb, in the olden days, in the bulb, why did we have a filament which is made up of tungsten? Because tungsten has the highest melting point out of all the metals in the world, out of all the metals in the periodic table. Tungsten has a very high melting point. Clear, everybody? Yes, guys. Is this clear, everybody? Clear? Yes? Yes? All right? Chalo. Okay, guys. Yes. Now, can you tell me that, see, everybody have a look. Manganese, technetium and rhenium, there is a sudden drop in the melting point. Why is there a sudden drop in the melting point, guys? Why do you see a sudden drop in the melting point? There is a sudden drop in the melting point because you see, what is the electronic configuration of manganese, guys? Manganese has an electronic configuration of 3d5, 4s2. See, the 4s2 electrons, they are paired up. So the number of unpaired electron, that has reduced by 1, right? In case of chromium, there were 6 unpaired electrons. In case of manganese, there are 5 unpaired electrons. So because there is a decrease in the unpaired electron, there is a quick correlation. There is a very nice correlation between the unpaired electron and melting point. Do we understand this? Do we understand this, everybody? Yes, guys. Clear hai? Very nice. So Now guys, coming back to it, the high melting point of these metals are attributed to the involvement of greater number of electrons from n-1d in addition to ns electron in the interatomic metallic bonding. In any row, the melting point of these metals rise to a maximum at D5 except for anomalous values of manganese and technetium. But I've just told you, right? Why manganese and technetium? Why does it fall? Why does it fall? Because of 3d5 but 4s2. The s2 or electrons, they are paired up. There is a decrease in the number of unpaired electron. Yes. Yes, so they have high enthalpies of atomization which are shown in figure 8.2. The maxima at about the middle of each series indicate that one unpaired electron per d orbital is particularly favorable for strong interatomic interaction. In general, greater the number of valence electrons, stronger is the resultant bonding. Since the enthalpy of atomization is an important factor in determining the standard electrode potential of a metal, metals with very high enthalpy of atomization, very high boiling point, tend to be noble in their reactions. See later for electrode potential. So, we will read about electrode potential later, but now let us talk about what is enthalpy of atomization. The answer is actually present in the name, guys. The answer is absolutely present in the name. So let me tell you everybody that what do you mean by enthalpy of atomization? What do you mean by atom? What is meant by atom? Atom is basically one single atom, right? Not in a molecule, one single atom. So basically you understand that when you take a metal sheet, let's say, when you take a metal sheet, let's say that we are taking an iron sheet, there will be iron, there will be plenty of iron atoms, right? Yes, there will be plenty of iron atom. Yes, right everybody? Very good. Now what will happen is, from here there are so many metal atoms, you want just one single atom to break down a bond and make it a single atom. That is called as atomization. And the energy that is required to break those bonds and make it into a single atom, that is called as enthalpy of atomization. Are we clear here, everybody? Yes, do we understand? So the enthalpy of atomization, so the enthalpy, guys, I have also logged in and I do not see any lagging, guys. I am not able to see any lagging. I have also logged in. Yes. It's not lagging, guys. It's not lagging, yeah? Yes, so we notice everybody that whenever the number of unpaired electron has increased, the enthalpy of atomization has also increased. That means that when the number of unpaired electrons are more, so what happens is the bonding is more, and that's why when you want to break it apart and you want to make it into one single atom, there is a very high enthalpy of atomization. Do we understand this? Yes. So unpaired electron is directly proportional to melting point. Unpaired electron is directly proportional to the enthalpy of atomization. Basically, the whole game is about unpaired electron. Do we understand this, everybody? Yes. Do we understand this, guys? Do we understand this? Yes. Chalo. Now, guys, moving on, everybody. Moving on from here. Let us talk about variation in atomic and ionic size of transition metal. Vineet Bacha, shh, I'll tell you. Please wait up. No, please wait up. I'll tell you. I'll tell you all of it. You will get all the answers. Chill. Just chill. Okay? Yes. Now, in general, what happens here is ions of the same charge. Okay? In general, what happens is ions of the same charge in a given series show progressive decrease in radius with increasing atomic number. Chalo. Now let us try to understand. Atomic radius, okay? Atomic radius is actually dictated by two factors. What are the two factors? Atomic radius, I'm telling you everybody, atomic radius is dictated by two factors, everybody. Number one is nuclear charge. Number one is nuclear charge. And the second number is the shielding effect, guys. And the second one is shielding effect, everybody. Yes? So what happens is initially you see that the nuclear charge. So okay, now everybody, let us have a talk about this, okay? What will happen if the nuclear charge increases? If the nuclear charge increases, then what will happen, everybody? If the nuclear charge increases, then the atomic radius will decrease. If the shielding effect increases, then the atomic radius will increase, right? If the shielding effect, who is shielding? Shielding effect is shown by the inner orbitals. They shield the last electron from the nucleus. At that time, the atomic radius increases. But if nuclear charge increases, atomic radius will decrease, everybody. Yes, very good, Harshit, very good. So now, everybody, what do we see? We see, everyone, that in general, ions of the same charge in a given series show progressive decrease in radius with increasing atomic number. The first line, everybody. As the atomic number increases, what is happening? The number of protons is also increasing in the nucleus. And if the number of protons are increasing, then what is happening? The nuclear charge is increasing. And if the nuclear charge is increasing, my dear student, then what is happening? Then what will happen? The atomic radius will decrease. Obviously, that is what we have just spoken about, isn't it? Yes, exactly, everybody. So, is this understood, guys? Is this clear? Is this clear? Can I get some la 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 or EPBT in the chat box? Easy peasy biryani tasty, everybody. Till now, everything is easy peasy biryani tasty. Yes, absolutely. So, this is because the new electron enters a d orbital each time the nuclear charge increases by unity. See, nuclear charge. This is nuclear charge. And it may be recalled that the shielding effect of a d electron is not that effective. Hence, the net electrostatic attraction between the nuclear charge and the outermost electron increases and the ionic radii decreases. Now, why do we notice that when we are moving from S block to P block, we see that slowly and steadily, the atomic radius is decreasing? That's because the S block, they have great shielding effect, guys. They have exceptional, amazing, shielding effect. The P block, they're a little less, okay? They're a little less shielders. Right now, D block elements, they are basically like, how do I say it? They are basically like, okay. So let's say, so if I wear my specs now, are you still able to see my eyes? Yes. Is it a shielding effect? Is this shielding my eyes? No, you are able to see my eyes, right? You are able to see my eyes. So the D block, the D orbitals, they are this kind of shielding. Yes, they are this kind of shielding. Basically, they do not shield at all. They are very poor shielders. So the last electron is very easily visible to the nucleus, and the nucleus is like, and it will hold on to the electron, okay? Yes, it will hold on to the electron, and hence the size decreases. But if it was S orbital, the S orbital, they're great shielders. The S orbital are basically, such shielders like this. Now, can you see my face? Can you see my face now? You cannot see my face, right? You cannot see my face now. You cannot see my face. So the S orbitals are like this. Now, if I teach you like this, there will be a disconnect between me and you, right? Because you guys are not able to see my face. You'll be like, what is this? Ma'am does not even show her face. Right? That is what you're going to say. But if you look at my face, if you look at the expressions, if you understand that, oh, ma'am is not well, oh, ma'am is fine, oh, ma'am is taking a nice class, oh, ma'am is taking an amazing class, then the connect is more. That is why we look at the chat. That is why we talk to you guys, isn't it? Yes? Right, everybody? Do we understand? This is clear? Yes. Okay. Now, however, the variation within a series is quite small. In this series, the variation is very small because what is happening? The electrons are actually entering the same last shell. From scandium to copper, if you notice, then what is happening? Scandium 3d1, 4s2. Vanadium 3d3, 4s2. Right? Titanium 3d2, 4s2. See, in d orbital, that is 3d. In the 3d orbital, one more electron are getting filled up. Hence, you see that the gap, that the range in that one series, it is very small. Guys, are we understanding? Guys, are we understanding, everybody? Yes. Okay. Now, an interesting point emerges when atomic sizes of one series are compared with those of the corresponding elements in the other series. Why so? The curves are shown in figure 8.3 and they show an increase from first 3D to second 4D series of the elements, but the radii of the third 5D series are virtually the same as those of the corresponding members of the second series. And this phenomena is a associated with the intervention of the 4f orbitals, which must be filled before 5d series of the elements begin. The filling of 4f before 5d results in a regular decrease in the atomic radii called lanthanoid contraction. So let's understand this, everybody. What is lanthanoid contraction, everybody? What is lanthanoid contraction, everyone? What happens is, now I was just telling you about the 3d, about the s orbital shielding effect, the p orbital shielding effect, the d orbital shielding effect, and the f orbital. So I just told you that the s orbital, they can shield someone like this, right? You absolutely cannot see my face, right? You absolutely